So, ya estamos. Okay, so welcome you all to this celebration of the life and contributions of Miguel Ángel Virasoro that we are having today, organized by the Physics Department of the School of Sciences of the University of Buenos Aires, with the support of the Mathematics Department and of the school as a whole. In this celebration, we will try to cover the various facets of Miguel, including the many areas that he researched, which is a very challenging task because he made key contributions in so many subfields of physics and mathematics, from string theory to neuroscience to econophysics. And he pursued this research with awesome depth and generated results of utmost importance, which were recognized by several awards. In particular, the latest one was the Dirac Medal that he received in 2020 from the ICTP in Trieste. But at the same time that he was so focused in his research, he also was a man committed to his time, who was not absent from what was going on around him. And so he took some positions, decision-making positions, and he stood with his beliefs, and that made him leave Argentina twice during the two latest dictatorships that we had. So, and then his trajectory was affected by all these decisions. And let me tell you a brief description of this trajectory. He studied physics here at the University of Buenos Aires, in this school that we are here in person now. And he obtained his licenciatura in physics degree in 1962, then his PhD in 1966 under the advice of Carlos Bolini. And in 1966, there was a coup here in Argentina that had a very violent event that occurred here in our school, which is known as the Night of the Long Sticks. And shortly after he defended his thesis, Miguel left Argentina and went on a postdoc to Israel, where he collaborated with Gabriele Veneziano, who is going to speak today. After that, he moved to the US, where he worked on he found what is now known as the Virasoro algebra. And today, the professor of mathematics of our school, Andrea Solotar, will speak about that. And in 1971, he came back to Argentina as an associate professor. He obtained that position through a concurso. And one of the members of the jury of that concurso is going to be present during the part of the activity today that is called Remembering Miguel Ángel Virasoro. This person is Daniele Amati. And then also at that time, after having obtained this position, he was appointed dean of our school in 1973 when democracy returned. And this will be also described at this part, Remembering Miguel, by Gabriel Vilmes on behalf of the program of history of our school. The democracy didn't last much, and violence started very soon, including during that democratic period. And Miguel was dismissed from his position as professor in 1974. And in 1975, he accepted a temporary position at the Institute of Advanced Study in Princeton. And then the dictatorship came in 1976. It was the cruelest one of our modern history. And so he moved to Europe, and then he stayed there. And in Europe, first he was in Paris, then in Torino, then in Rome. He started to work on complex systems and started his long collaboration with Marc Desart, our first speaker today, who is already connected on Zoom, and with Giorgio Parisi, who obtained the Nobel Prize in Physics last year, who will close all the event today with another talk. There in Rome, he also started to look into these complex systems problems, particularly spin glasses, but then on neuroscience. And we will have a talk on neuroscience by a professor of our department, and also became interested in econophysics. While he was in Italy, he was appointed director of the International Center for Theoretical Physics of Trieste. He was the first person appointed to that position after the death of the founder, Abdus Salam. And he was the first Latin American ever to be director of that center. And today we will have Fernando Quevedo, who was director. He's a Guatemalan physicist who was also director of the ICTP, talking about what imprint Miguel left at that institution. And well, then he retired from Rome in 2011, and decided to come back to Argentina. And he started a position, he got an honorary position as professor of Universidad de General Sarmiento, which is located in one of the poorest districts of the suburban areas of Buenos Aires, because he thought that there he could have a much deeper impact. And there he started discussions of a complex systems group, and some people that participated of that discussion, those discussions will also contribute to our event today. And talking about impact, many people that have told us about their recollections of their interactions with Miguel told us about the impact, the deep impact that Miguel had on their lives and on the decisions they made regarding their career trajectories. And so that's why we want to celebrate not only the contributions to science, but also his impact to so many people. And that's why the school has approved that we give the name of Miguel to the classroom where we are now. I hope that you enjoy this meeting and also leave it with your soul touched by all what Miguel has done. I will leave the floor now to Hernan Greco, first to the Vice Dean of our school, Luis Baraldo, who is here with me, and then to Hernan Greco, who is the chair of the physics department of our school. Thank you.
Thank you, Silvina. Hello. Well, thanks, Silvina, mainly for organizing and this initiative. In the name of the school, our Consejo Directivo decided to name this classroom with the name of Professor Virasoro. And I think that is very fitting. I will keep this brief because we have a packed schedule, but I just want to highlight that later we will talk about the physics, his scientific contributions, and and also as a teacher and as a colleague. But I want to highlight that Professor Virasoro was a man of his time. He was really compromised with several projects, and he also put a lot of effort not only in participating in these activities, these projects, but also show a big commitment in organizing them. I mean, putting the time, knowing that the institutional life is very important. And this not only shaped his academic career, but also shaped his life, as he has to move frequently, as Silvina already told us. So I think it's fitting that the Consejo Directivo has decided to name this room with his name, because it will be a reminder for us, the faculty members of our school, that we should share his same commitment to our time. We have our time, we have our challenges, but we should try to follow his steps. Our school has been lucky in having many professors, and we have their names there to remind us which is our duty, our challenge. So I think it's very fitting that this room will have his name. Thank you.
Hello and welcome, everybody. So it's my great pleasure as a head of the physics department to give you this last welcome to the Virasoro seminar. It's very difficult to summarize Miguel Angel's impact on science, on the community. So I will briefly give you, let you go into the schedule, because as Silvina has already pointed out, the diversity of his thoughts towards all areas of science can be seen in the diversity of the topics that we are going to cover today. The impact on the colleagues and in the improvement of science can also be seen in the amount of people that wanted to contribute today to current seminar, and also that email us at the physics department when we had to lament his death. And finally, his impact in the community can be seen also in the desire of the University of Buenos Aires, the School of Science of the Physics Department, to honor him, not only with this seminar, but with this permanent naming of this lecture room in his honor. So with that, just final words, I would like to thank all the organizers, Silvina, of course, Pablo Valenzuela, Pablo Benini, Gustavo Lozano, for the great work that they have done to assemble this very interesting schedule that is going to cover not only all different areas of Miguel Angel's contribution to physics, but also his political and institutional contributions and his thoughts, because as Baitin was just saying, he is a man of his time. So with that, I thank you all for coming here, and we hope that we enjoy the day together.
So Mark, if you want to share your presentation. Okay, so we are 1 minute ahead of schedule, but I will make the presentation, and I guess it will be 9:15. So it's a pleasure for me to announce the talk of Marc Mézard. Marc is a renowned physicist who made very important contributions in the area of complex systems, particularly in the study of spin glasses. Until very recently, he was director of École Normale Supérieure in France, and now he's affiliated with Bocconi University in Milano. And as I told you before, he was a long-time collaborator of Miguel and of Giorgio Parisi, and he will give this talk titled Disorder, Frustration, and Beyond. So thank you, Marc.
Thank you.
The floor is yours.
Thank you very much, Silvina, for this introduction, and thank you above all for organizing this this day. It is very important, I think, to remember our friend Miguel. I should say that it is a very special year also. It is a special year because, as you mentioned, this year, this year was the year of the award of the Nobel Prize to Giorgio Parisi. Unfortunately, Miguel could not be here to witness that great moment. Miguel was thinking a lot of how much he thought that it would be deserved, and I regret that he could not witness that. I had prepared this slide for a talk I gave at the occasion of the Nobel Prize of Giorgio. I had prepared it. It addresses a few questions, but what I like in this slide is, first of all, the fact that Giorgio is lecturing. He's happy to lecture, one sees it. And he's lecturing about something which is very dear to my heart. Is for those who know that, he's lecturing about the geometry of equilibrium states in spin glasses, and particularly about ultrametricity. In an ultrametric space, the states are like on the leaves of a tree. And so all triangles are either equilateral or isosceles with an acute angle. And that is clearly what Giorgio is telling about. Why is it so dear to my heart? It's because when I started in research, I was doing my PhD, and Miguel came to École Normale, and he wanted to have to see some new topics, and he wanted to look at statistical physics problem. I was beginning in statistical physics myself, and he told me, well, let's let's read the papers together and let's try to see what we can do. And the first thing that we did was to try to understand this famous Parisi paper on replica symmetry breaking that nobody understood. And soon after that, after some months of work, we realized, and also together with Giorgio, we realized that the replica solution was hiding this ultrametric structure. And so that there was a whole geometric perspective to the problem. And that is the beginning of my long and deep collaboration with Miguel. So on the occasion of this Nobel Prize, I tried to have a long-term perspective to see exactly what has happened in the last 50 years, let's say. Well, if one thinks backward, one could see more or less that statistical physics was created, roughly speaking, 150 years ago. It was a major step at that time. It was giving up the deterministic description of nature, giving up, in some sense, the idea of flowing particles using Newton's law, but introducing a probabilistic approach. And on this scale, it's 1/3 of the scale, which is 50 years ago. There was this creation of a new branch of statistical physics, the one of strongly disordered systems. And this branch of statistical physics is maybe not always realized. It was posing several formidable challenges. There was a major step by Giorgio in 1979, the replica solution of the mean field theory of spin glasses and the breaking of replica symmetry. And in the 80s, there was the following up the physical interpretation of the replica solution, alternative solution using a more physical approach, the cavity method, and that opened the way to rigorous mathematical proofs and much beyond that. And that is really the things on which we worked together with Giorgio Parisi and Miguel Virasoro in the 80s, was this elaboration of a new framework and also pushing the frontiers of the applicability of spin glasses to many other fields. So this brought us to write this book in 1987, called, often the students call it Beyond. And this is a small small part of the introduction of our book, where we say in particular, we are firmly convinced that the techniques developed for spin glasses, the replica theory, the tap approach, and the cavity method can be applied to a myriad of other problems that otherwise are very difficult to handle. And this, I think, we are witnessing that every day. And I will briefly evocate some of the fields in which these techniques are being applied or have been applied. And it's incredible. It was named the cornucopia by Phil Anderson at some point. So I think that this prediction, at least, was certainly correct. And in the last part of this introduction, we also said, we think that the moment is ripe to try a presentation of these techniques that demonstrates their essential simplicity. The essential simplicity, I think it is correct also, but we had hard time to demonstrate it. So it has remained something which is a relatively sophisticated apparatus. So one could study and ask, why is it so important to develop this study of disordered systems? And how is it that the study of spin glasses opened a whole new field of research, expanding much beyond the simple problem of alloys of copper and manganese or of gold and iron, which were the initial samples of spin glass on which one had detected a magnetic anomaly. And in retrospect, I would like to understand the four main challenges that had to be met in order to develop this new branch of statistical physics. So the first challenge is the fact that one has to study ensembles of samples. So in a spin glass is a system of interacting spins, typically manganese impurities in copper. So the manganese carry the magnetic moment. Imagine, to simplify things, that they are just easing spin. They have two states, plus or minus one. They interact by pair. So you have the typical easing interaction energy, which is the sum of a pair of Jij, SiSj with a minus sign. And the particularity of spin glasses is the fact that the coupling constant, the interaction constants Jij between the spins I and J, it depends on the pair I and J. In particular, in metallic spin glasses, for instance, it depends on the distance between the two impurities. It oscillates with distance. So depending on the distance, depending on the pair IJ that one looks at, one can have either ferromagnetic interaction favoring the alignment of the spins at low temperature, or anti-ferromagnetic interaction favoring the anti-alignment of the spins at low temperature. And so this makes life more complicated. It means that there are conflicting interactions on the one hand, but it is also extremely disordered. And in particular, each sample is different. That is, a sample is given by the set of interacting constants, Jij, the set of all the interacting constants. And for a given sample, we have a given energy and a given Boltzmann measure. But of course, another sample will have different positions of the impurities. It will have different interaction couplings. And so it will have a different energy. In energy here, I wrote it as with a J index. It means it depends on the sample which characterizes the J, the couplings. And so one needs to understand what happens in a typical sample of copper manganese. So typical with respect to what? With respect to a probabilistic ensemble. And so a probabilistic ensemble, which could be the distribution of positions of the impurities, for instance. So here we had to develop a theory that would be able to understand what are the self-averaging quantities, which are identical in almost all samples. We know some of them experimentally, like the magnetic susceptibility or the specific heat. In general, many of the thermodynamic properties are self-averaging. But there are also other properties which are not. A tiny difference between the energies of the ground state and the first excited states, for instance, they are totally sample dependent. So we have two notions of disorder when we address spin glasses. The first one is the fact that we have quench disorder, and the second one is the usual thermal disorder. So the quench disorder is what describes the sample, but this gives me the set of coupling constants. And the thermal disorder is the Boltzmann law. And really, one of the first papers that we wrote with Giorgio Parisi and Miguel Virasoro was really about understanding this, what quantities are self-averaging, become in the large size limit, they become independent of the particular realization of the sample, or what are other properties which still depend on the sample. The second challenge is in homogeneity. In a spin glass, every spin is in a different environment. So every spin has a different magnetization. And in particular, technically, it has a very big impact. It means that there is not a single equation that can represent the sample. There is no, in economics, one would say there is no representative agent, because every agent has its own environment, has its own strategy in some sense. So when Thouless, Anderson, and Palmer in 676 wrote the mean field equation for this system, it's not a mean field equation for one parameter, but it is a system of n coupled equations for all the local magnetization, for all the capital N, the number of spins, one magnetization per spin. So it's already a major simplification from the original problem, which is a probability distribution over 2 to the n configurations. But of course, then one has to still to understand what is the content of these equations, what are the statistical description of the magnetization of the local fields. And this is what can be done through the development of the cavity method. The third challenge is the existence of rough landscape. If you plot the energy versus configuration space, so it's a very naive one-dimensional plot here of a function which lives in a very large dimensional space, one can prove that it has a very shaky behavior with several states, many states which are very close to the ground state in energy. They have the same energy density. The energy per spin is exactly the same in the thermodynamic limit, but they are very different from each other. So these are the famous pure states of spin glasses, in contrast with the ferromagnet on the right-hand side of this figure, in which we have only two pure states. So understanding these ground states, these many ground states, understanding the structure of metastable states is also a major challenge. That's where ultrametricity comes in. when you go fine-tune into the description of this problem. The landscape also forces us to invent new order parameters. If you study ferromagnets, you remember that there is a very important phenomenon, which is that in the thermodynamic limit, there is spontaneous breaking of the up-down symmetry of the spin. It means that if you put your system in a small magnetic field, uniform, then you take the thermodynamic limit, and then you take the limit of the magnetic field going to 0, you will find two different results depending on whether the small field is up or is down. And this gives you the symmetry breaking in a ferromagnet. In a spin glass, you have something a bit similar in principle, but there is one such magnetic field on each side, and one for each side and one for each state in which it can condensate, one of these many states. So this is extremely complicated because this kind of symmetry breaking parameter, this BI of the state alpha, in order to find it, you already need to know the magnetization in the state alpha. So you already need to solve a very complicated and coupled system. So the idea to address this complicated question, one can at least understand in retrospect that this is one way of seeing what the replicas are doing. The idea is that for us, it is extremely complicated if I just give you the Hamiltonian, if I give you the energy function, the JAJ, the coupling constants, to say where are the ground states, where are these states MI alpha, where the system will tend to spontaneously polarize. We don't know that, but the system knows it. And so the idea is to take another system and to use it as a conjugate field to the first system. So basically we can have two configurations, the configuration of spins S1 and S2. They are both generated at equilibrium, and the distribution of the overlap, Q, which is the projection of S1 to S2 defined on this slide, this distribution P of Q is really the order parameter of the spin glass. And that is what replicas are computing, actually. And the fourth challenge is also a very difficult one, which is non-equilibrium properties. In spin glasses, we see slow relaxation, we see aging. It means that in the spin glass phase, the system never reaches really the equilibrium. So the non-equilibrium effects are crucial. These are dynamical effects. And a big question, and something on which there has been a lot of progress, was how to relate the equilibrium property to the long-time non-equilibrium properties. So this means understanding the dynamics from the landscape, understanding the fluctuation-dissipation relations. So with this development of the theory of spin glasses, on which Miguel was so much one of the key person, it requested to be able to address these main problems, study ensembles of systems, study systems in which each spin is different from all the other ones in the sense that it sees a different local field, with the consequence that they freeze in random directions, studying rough landscape with many minima of the energy and difficult to predict and find the minimum of the energy, and also be able to relate this rough landscape to the strong long time out of equilibrium dynamical effects. All this, I must say, has fascinated us a lot in the 80s, and since then, it appeared rather clearly that it was an absolutely fascinating subject, very rich, a cornucopia of new ideas, of new concepts and methods, but it was useless at the same time. That is, we never found, nobody found really an application of spin glasses in everyday life. It is a very generic problem. So I will flash a couple of slides so that people can see a little bit the scientific domains in which these ideas have been applied. It goes from physics of structural glasses, where it took some time to understand how to apply these ideas to structural glasses, but now there has been a lot of progress which has been made. Neural networks and the theory of the brain, learning theory, inference and statistics, machine learning, very popular these days. information theory, error correcting code, signal processing, optimization and computer science, heteropolymer and protein folding, evolution, biological evolution, economy and finance, and all the aspects of mathematics related to this, which have become quite important in recent years. There have been also on this occasion the development of new techniques, let's say, related to replicas, to the cavity method, to the tap equations and their use algorithms, interpolation method, which have been very important in order to prove the results that were kind of guessed, intelligently guessed, I would say, from the replica study. And a lot of concepts have appeared on this way, and have become really everyday tools for the people who are working on this field. So let me give you one example. I like this example because it is a kind of very concrete one, and it's also an example of this beyond, the beyond that I was mentioning at the beginning, that it appeared very clearly, and I insist on that to Miguel, it was something that mattered a lot, that in some sense, this elaboration of the statistical physics of this ordered system, it could be a building block to understanding important other scientific problems in other domains. That's why we put this name beyond in the title of our book. So one example of the beyond is the applicability of some methods of statistical physics and spin glasses to important problems in computer science. And in computer science, there is one problem which is particularly important, which is satisfiability. It is important because it is the first problem that has been shown to be NP-complete, NP-hard. So it is really at the core of the definition of and the discovery of NP-hardness. So it's very easy to formulate. It's a problem of computer science in which you are given n binary variables. They could be 0 or 1, meaning false and true, respectively. And you have constraints between these variables. So each constraint could take 3 of the variables, let's say, and it is the OR of the variables or their negations. For instance, here I have written the constraints x1 or not x2 or x3. So this constraint will be satisfied except in one case. Among the 8 configurations of the variables x1, x2, x3, there is only one which does not satisfy the constraint. It would be the case in which x1 is false, x2 is true, and x3 is false. So in general, in satisfiability, you are given a series of constraints like that, of clauses. And the question is there a configuration of the variables which satisfies all the constraints? It turns out that not only satisfiability is the core of the NP completeness, but also 3-SAT, that if you restrict to clauses of length 3, it is also an NP complete problem. And if you want to generate hard instances, typically hard instances of satisfiability, one way is to generate random 3-SAT formula. This is obtained by generating each clause with 3 randomly chosen variables among the sets of xi bar. And experimentally, if you look, you generate such a formula, you take n variables, you generate randomly m clauses between them. Each clause contains 3 variables or their negation. And you look at what is the probability that all the m clauses are satisfied. And you look at it. Here it is written as a function of alpha, which is m over n, which is a number of constraints per variable, the density of constraint. And you see that when the size of the system increases, you find that it seems to go to a threshold function. And in fact, finite size scaling have been also studied here. And experimentally, there is a phase transition. And phase transition, which is such that for large n, for large size problems, a typical instance will be satisfiable for alpha less than the critical value, alpha c, and unsat for alpha. Unsat means that there is no solution for alpha larger than alpha c. Using the methods of statistical physics of random systems, of spin glasses, developed in the last 25 years, it was possible to write self-consistent equations, functional equations that could lead to the prediction of the critical value of the SAT-unsat transition. So for 3-SAT, it is 4.2667, and one could add more digits if needed. But more interesting, what happened is that in this problem, there is a phase diagram which is richer than expected. So here in the bottom figure, you see a kind of cartoon of the phase diagram in function of the single parameter, which is the density of clauses, alpha c, the number of constraints per variable. So you have the SAT-unsat transition, which is at a critical threshold of 4.267. But it turns out that below this threshold, there are really two phases. At small alpha, when there are not too many constraints, you find that in green, you should imagine that I have colored in green all the configurations which are satisfiable. And basically what you find is a big connected cluster. That is, you can go from one satisfiable configuration to another one by flipping some variable. And so by local move, you can move from one solution to another. It's a connected space of solution. And then at a very well-defined alpha, which is alpha d on this figure, which is called the dynamical threshold, there is a phase transition which is geometric. And it is related to the fact that the solution, the configurations of the variables which are solutions, they become clustered in these green clusters, which are very separated from each other. And so you have, these are zero energy states. The energy is the number of violated clauses. So you look at the green solution, which are zero energy states, and they are clustered and they are very, very separated clusters. That's a geometric phase transition in large dimension. On top of that, of course, there are other clusters which violate some constraints. So there are also metastable states. But this prediction of this intermediate phase, it is a glass phase. It is a realization of a dynamical glass phase in the sense of spin glass theory. And it is one in which one can really, in some sense, visualize the existence of the metastable states and of the many states and the breakdown of the replica symmetry. Another topic on which there has been a lot of work in recent years has been the machine learning and the statistical physics of machine learning. So in machine learning, you want to find an algorithm, let's call it a machine, which takes an input, could be an image, for instance, and gives an output. And for instance, well, people have spent a lot of time training machines which are able to distinguish if there is a cat or a dog on an image. So you put an image of an animal, and the algorithm should tell you it is a cat or it's a dog. Present days, this is done through deep networks of artificial neurons. So each circle here is an artificial neuron. It's a very elementary system in which the neuron will take the inputs from the incoming neurons. Let's say 3 incoming neurons here. It takes the weighted sum of the inputs. The input of the neuron X1 is weighted by a parameter J1, which is exactly like the synaptic efficacy between neuron X1 and this new one. Same for X2, same for X3. Takes this weighted sum and applies a nonlinear transformation, which could be here a rectifying linear unit, or it could be a sine function. And so this network here, it is a network which is described by a certain number of parameters. Actually, there is one parameter for each line on this network because there is a synaptic weight on each line. So it is described by many parameters. In modern networks, you can have millions of neurons, much more even, hundreds of layers, 10 million parameters I wrote, but I think now it has been outdated. It is probably billions of parameters. And the question is, the idea of machine learning is that you will not try to determine yourself the value of each of these parameters. It would be a very daunting task. Instead, what you do is that you train the system on huge database. That is, you take a large database of labeled images, many images of cat that you know they should be labeled as cat, many images of dogs. And basically, you will try to find the set of synaptic couplings that are such that for each image in your database, you give the machine gives the right label. And you do that by simple gradient descent type algorithms. So here is the formalism. You have the input, that would be the image. You have the set of weights, that would be the synaptic weights. You have the output, that could be the label, cat or dog. And you have a database. And the database is n examples of pairs xi mu, y mu. Sorry, capital P should be the same as small n here. And you have an optimization problem, which is find the synaptic efficacies that minimize the errors that are done on the training set, on the database. And you can turn that into a problem of Bayesian learning, in which you want to find the weights, you want to find the coupling constants, the synaptic efficacies, and you put a Boltzmann weight that will minimize the error when beta is large. Of course, there is then the second step, which is when you have generated optimal weights, W star, you want to understand the generalization properties. That is, you want to measure the generalization error. How does the machine perform on new images that it has never seen? Does it only memorize, or is it able to generalize? One very standard example, which is in some sense a building block of all that, is what happens at the level of one neuron. One neuron receives the input from n other neurons here. And in the perceptron, you just take the sign of w dot psi. And you can study the learning problem. And you could study, for instance, the capacity, how you can memorize random patterns. Or you could also study what is called the teacher-student problem, in which you imagine that the labels have been generated by a teacher. The teacher has its own weights, and it generates the label by sign of W teacher times xi mu. And the students is learning the weights. And of course, if he finds the same weight as W tilde as one of the teacher, he will get the exact answer. But the question is, in learning, how does it get closer and closer to the teacher? And this is something that has been studied quite a lot. And if you look at the generalization error, what you find as a function of the alpha, which is number of patterns in the database divided by n number of neurons, and you find that the error follows this curve here. And then theoretically, in principle, one should follow the red curve. That is, at some point around 1.24, there is a phase transition. And beyond that, you have seen enough example that the student can find exactly the same solution as a teacher, the case of binary weights. It turns out that in between, there is, if you do it algorithmically, and in particular, if you apply the equivalent of TAP equation, Thouless-Anderson-Palmer equation, you apply this equation to study the system, you will find that the TAP equation, they give you the right solution only beyond 1.5. So there is an intermediate phase in which the TAP equation will not be enough to find a solution that we know exists. So understanding the landscape of deep learning, that was the example of the perceptron. It has been known for long. We have many more challenges now, and the challenges that are being faced at the moment is, it's a very interesting moment, because it's a moment in which really deep networks are revolutionizing a lot of technological problems, and we know that a lot. I mean, everybody talks about AI and AI application. At the same time, the theoretical landscape has not evolved such much, and we need to develop some new theoretical tools. In particular, some questions are related to the energy landscape that I was mentioning before, the energy landscape of spin glasses. It seems that in deep network, the landscape is not like this. There are many, many solutions to the learning problem, and starting from a given point, there is typically a solution which is not very far from it. How does it depend on the problem, on the database, on the architecture? How the flatness of the minima relates to the capacity of generalizing? These are very big questions that people are studying. So there are two main issues, algorithmic and theoretical. And it is really a very important moment. And I think that it is a moment at which one really starts to, one should develop new tools of statistical physics to address these important problems of AI. modern AI. Just to give you in less than 5 minutes, one example of the challenges that we are meeting, it relates to the structure of data. In all the work that has been done using statistical physics, people were using artificial database ensembles, my famous disordered system ensemble that I was mentioning in my first challenge at the beginning, that are IID variables, independent, identically distributed variables. Instead, the data on which a neural network is trained is not at all IID. For instance, one of the very basic databases is MNIST, a database of 70,000 handwritten digits. And each digit is has 28 square pixels. So it is a vector in a 784-dimensional space. Okay, but it's not at all IID. In fact, if you think of what you can draw in such a space of 28 square pixels, you can draw a lot of things. And you can ask, are there some special properties of the images which are handwritten digits? It's not so easy to answer this question, but one thing that can be done is study the effective dimensionality of the subspace, which is a manifold in which the handwritten digits live. And in order to do that, one can use some physics tools like the ones that were developed in particular initially by Grasberger and Procaccia to study the dimensionality of strange attractor. That is, you put p points in a space of dimensional d, and you find that typically the nearest neighbor distance between these p points scales like p to the -1 over d. This allows you to estimate d. And in fact, in MNIST, the data lives in 784-dimensional space, but the effective dimensionality is more like 15. So it is a folded manifold. It's not a linear subspace. It's a folded mass subspace, but of relatively low dimension. And this is also true for each individual digit. And it's also true for other databases, like, for instance, this CIFAR database. It lives in a manifold of dimension around 35. So the big new frontier that we are facing at the moment is understanding ensembles of samples with structure and correlation. And I see that the time is running, so I will not give you the details of how one can address these ensemble. I will just list, let's say, what can be done. In the usual spin glasses, we have these coupling constants between the spins, which are typically independent, identically distributed. Is that the case of Edwards-Anderson or Sherrington-Kirkpatrick model? In memory neural networks, Hopfield networks, on which Miguel did some so much work, then we start to have some correlation. That is, this Jij, the coupling constant, they are elaborated from the dot product of some internal activity of the neurons. And so this is how you memorize patterns. Then one can also study rotational invariant patterns, or one can move also to memory networks in which each pattern has a certain hidden substructure. And then the last step that was also taken was to try to model data in which there would be hidden manifold, in which the data would live in one of these manifold subspace. So I will not go too much into these details because it would take me too long. I will just jump to my conclusion. I think that modern artificial intelligence and machine learning, it's really an incredible technological revolution, but it's also looking for a theoretical framework. There are many theoretical questions that are open. And it is based, of course, the big ingredient is the fact that one uses systems of very large size. And we use a lot the fact that we have a lot of computing power, much more than what we had in the 80s when we first studied that with the physics methods. And we also use very large data sets. So I think it's a very nice field in which statistical physics of the systems can be brought to bear. But then one needs to develop new serious extensions. One needs to face more challenges, more beyond the 4 challenges that I was mentioning at the beginning. One needs to find how to study learning and generalization in extensive multi-layer networks, and how to handle structured data. these are at least two major extensions of statistical physics that one has to develop. Also, I have no time to mention that now, but these new developments raise many questions in connection to new developments in neurobiology, where they also find the structure of manifold of data. And I think that the success of modern machine learning algorithms in language processing, for instance, it challenges again, let's say what we call intelligent behavior, and it poses a lot of interesting questions also on a kind of larger scale and seen from above, let's say. And I really wish that Miguel would be here, because I'm totally sure that he would have really liked so much discussing all this, and I would have so much liked to discuss this with him, and he would have had a lot of inputs on all these topics. Thank you very much for your attention. We need to take questions, of course. I don't hear anybody, but
thank you, Mark. Can you hear me?
yes.
Okay. Thank you for the very interesting talk and widespread touching a lot of aspects. I don't know if there are any questions here from the people in the class. And I have a comment from YouTube. Let me check also if there is a question here. So Sarah Socha, she said that on the hidden manifold of data, the image name database
where images have 150, 528 pixels, the intrinsic dimension of the manifold has been estimated to be 45. That's a comment of Sarah.
Thank you.
And I don't know if I don't see any questions on the Zoom or on YouTube. Pardon me? So let me ask you something about neural networks and deep learning. And can you hear me okay? Because
I hear you so and so, but yes, I try to.
Okay, so it's not so good. Sometimes, how much theory you can make of that? Because many times it's a black box and that works, and nobody knows exactly why. And so you feed it with examples, and how much the results you get depend on those examples, and how much you can extract from a more general view and get a theory. You can say something about that.
It's a very interesting. It's a major question that you are asking. My own view is that it is extremely. I mean, there are two types of theoretical approach that you can use for neural networks. More than two, but let's say two big families. One family is some kind of universal bound, let's say learning theory. Learning theory tells you it's basically a development of statistics, which tells you if you have seen so many examples, then there is a kind of absolute bound that you will never have a performance better than something. And it's a function of the number of examples that you have seen. It's a decreasing function. And for instance, the standard bound tell you that the error decreases like 1 over square root of alpha. But these are always worst case analysis. They are worst case analysis that will apply to any situation, any database, any function that you want to learn. And so they turn out not to be very relevant. And so the other way of trying to develop a theory is to have something that depends on an ensemble of database. I mean, a theory for a given database, it's extremely risky because you may soon get into fitting some details of a database that are unimportant. So what we should try to understand is what is a good ensemble of problem. And this is where I think a lot of work is needed. That is, we have started a little bit to do that with the hidden manifold data, with the structured data. In my opinion, there are the main steps are to develop ensembles of problems in which data lives in a hidden manifold, is combinatorially structured, in the sense that data, the typical data, it is based on combinations and combinatorial articulation of various items, and this is, I think, some of the major challenge that we have to do before even we can start to apply the statistical physics ideas. And I think it would be a major step for developing a theory.
Hi, Mark. Thanks for your talk. Can you hear me properly? Yep.
Yes, very good.
Following Silvina's question, actually, I was wondering if you can provide some insight regarding what does the content of the actual network that is found after learning regarding the problem that we are analyzing, right? Because following Silvina's question, it seems that neural networks just provide us a way to, for example, it's very good for classifying, right? For example, but what does the actual connections that are learned can tell us about, for example, a physics problem or a problem in neurobiology or a problem in biology? So what can we learn for the actual connections that are learned and not just from getting the output?
Well, one gets quite some interesting information from the internal representations. Let's say you can one exercise that has been done many times is to look in one of these neural network, for instance, the ones which are trained on images, let's say some task on an image, and you want to try to understand what is, you take some neuron inside the system, and you try to see with the synaptic weight that have been learned, so they are fixed, what would be the input to which this special neuron is most sensitive. And what you find is that it depends where the neuron is located. If it is located in the first layers, quite close to the original image, then it is sensitive to very basic things like the existence of an edge or something like that, an edge with a certain orientation. Exactly like what we see in Hubel and Wiesel in the cells in the first visual areas of the brain. Then when you go deeper into the neuron, into the network, to deeper layers, you find that a given neuron will be more sensitive to some pattern which has more structure, which is a larger scale. For instance, first of all, it goes to a larger scale. That is, that in the first layers, it's mostly sensitive to something local. Then it goes to larger scale, and it goes to something more elaborate. Maybe when you go deep into the network, you will find something that is sensitive to a structure which looks like an eye, like a nose, like an ear. And so that is how you can see how gradually there is, I mean, people have been using these ideas of renormalization group, of course. That is, when you go deeper in the network, the neurons become sensitive to larger scale structures, of course. But that's not enough in itself to build a system that works. And so, well, I think this is really the thing that is the most important. Then one can also fix an internal representation and see how, from this internal representation, what could be the various outputs that would be created. And that is something that is very interesting. I think it's one of the new developments that really had not been around in the 80s, which is the generative aspects of neural network. How you could ask of a network not only that it classifies like I was doing before, but that it can also generate pictures, let's say, and that it could does it generate a picture which looks like a cat or not, and so using it as a generator is also something which is very a new area which I find very interesting.
Thank you, Mark, for the very interesting talk. And so now we will move on to the next talk by Gabriele Veneziano. And if you're interested today, I think at hour 12, which is 5 in Europe, there is going to be a talk on deep learning and cognition. So that would be very interesting to listen to. So we welcome now Gabriele Veneziano. If you want to start sharing your presentation.
Yes, I'll try. Can you hear me, first of all?
Yes, yes, great.
Okay, I'll try to share.
Okay, so in the meantime, I will introduce you to the public here and to the public on YouTube. Gabriele Veneziano is a theoretical physicist who is considered the father of string theory. He conducted most of his scientific work at CERN in Geneva, Switzerland, and then he held the chair of elementary particles, gravitation and cosmology at Collège de France in Paris. He worked with Miguel around 1967, and he will give in Israel, and he will give the talk a wonderful 5-year-long interaction. Thank you, Gabriele.
Thank you. Can you see the screen already, or?
Not yet, not yet.
Not yet. Wow, that's a moment. So I have to find share screen. Okay. Okay. Now you can see something of my screen?
Oh, we can see you.
Okay, now I'll put full screen.
And now you should do the play or something.
Yeah. Okay.
Great. That's fine. Thank you.
Okay, let me. All right. So let me thank the organizers of this interesting and very meaningful meeting. It's an honor to be able to give this modest contribution to a dear friend and a very important collaborator. So I will concentrate my presentation on this 5-year period that during which we first collaborated and then we interacted quite strongly together. Let me, if it scrolls, sometimes it has some difficulties. I cannot scroll. Sometimes I can, it doesn't work. Yeah, I don't know why, when I'm in full screen, sometimes it doesn't scroll easily by pushing the arrows or anything. Ah, okay, now it does work. So it went on. Wow. Oh la la. Can you still hear me? Hello?
Yes, we can hear you.
Oh, you can still hear me.
I don't know if they can hear you, but I can.
Okay, now it works. So let me start with telling you how our word lines crossed very luckily around the winter of 1967. So let me first tell you about my own word line. I finished a master in physics at the University of Florence at the end of 65. And then I decided to move to the Weizmann Institute. At that time in Italy, there was no PhD program. And we had interaction with some physicists in Israel. So I decided to apply for a PhD course there. And I arrived there in the fall of 1966. At that time, my official advisor was Professor Lipkin, but in practice, it turned out to be Hector Rubinstein, an Argentinian also. He had worked in Paris before accepting a professorship at the Weizmann Institute maybe a couple of years earlier. And Hector and I immediately started to work together. We wrote a couple of papers on a subject called current algebra. And eventually I graduated. I got my PhD at the end of 1967. Miguel's work line was quite parallel. Of course, much more, how can I say, hectic or dangerous, because in June 1966, I don't have to remind you, there was a coup d'etat in Argentina. Academic people became the target of the military junta, and many professors emigrated. But Miguel at that time was working on his PhD thesis, so he managed to finish it working at home because he could not go to the university, and eventually graduated at the end of 1966. So a year before I graduated at the Weizmann Institute. At that point, he left Argentina, accepting an invitation by Hector Rubinstein, and he moved also to the Weizmann Institute. So in a sense, Hector Rubinstein was the lens that deviated our work lines and made them coincide. So as early as beginning of 67, the three of us formed a very close and friendly team. It was extended outside work to the respective families. Now, you know that in June 1967, we were all there witnessing the Six-Day War in Israel. It was a political turning point for Israel, for the Middle East. I still remember discussions about politics with the local scientists, which tended to be pretty hawkish at the time. And I think the three of us were considered some dangerous leftists of some sort. On the other hand, the turning point, not in politics, but in research, took place a couple of months later when we heard, I was myself in Erice, in Sicily, to a summer school, about the so-called Dolan-Horn-Schmidt duality, and a possible bootstrap based on it. Bootstrap, for those of you who don't know, it's a word for solving a problem by merely applying self-consistency. Then in September 67, I was momentarily back in Florence visiting the family. And before going back to Israel, I discussed this news with Professor Ademollo, one of my previous professors there, and we decided to keep in touch. He was going to move soon to Harvard as a visitor for 2 years. Then soon after, back at the Weizmann Institute, while Marco Ademollo was at Harvard, and we had good communications, but as you can imagine at the time, they were extremely slow. You know, we'd send letters, which would go for weeks before coming back and so on. But anyway, it worked more or less. And the enlarged collaboration started to work very enthusiastically on this so-called duality bootstrap. I should mention another line of research, though. Although this duality bootstrap took most of our research activity, I guess as a byproduct, if I remember well, of Miguel's PhD work, the three of us also worked on a problem, on a different problem, which had to do with the effects of a possible compositeness of otherwise thought elementary particles. We argued that certain form factors would decay at large momentum transfers with an inverse power law, and that the power would be simply related to the number of constituents. The larger the number of constituents of these composite particles, the faster would be the decay of the form factor. We, or I guess rather Hector, learned that Daniele Amati and Roberto Yengo had been working in Trieste on the same problem. And so we started discussing with them, exchanging ideas and results, and eventually a paper with all 5 authors, 3+2, was published. I think it was a very interesting precursor of what people did much later in so-called QCD, or quantum chromodynamics, which is now believed to be the correct theory for strong interactions, hadronic interactions. It was also the beginning of a lifelong friendship between Miguel and also myself and Daniele. Now, let's go back to the bootstrap. In the winter 1967-68, we also took advantage of a very useful and encouraging visit by Sergio Fubini, of which I luckily kept a nice picture. So you can see Sergio Fubini, older than us, sitting in the middle, and the 3 of us sitting very close to him and very attentively listening to what he was saying and looking at what he was writing. So you can see Hector and see myself and Miguel here standing. The other 3 guys, 2 of them I could identify, did not look as interested as we were. Subsequently, we published a number of papers showing how a simple parametrization of the process, this is a scattering process among strongly interacting particles, could satisfy the 2 sides of this duality bootstrap equation with amazing accuracy that we could actually systematically improve by adding some simple improvements on the object itself. Now, as June 68 arrived, all 3 of us were going to leave Israel for different destinations, basically to take up postdoctoral position. Miguel went to Madison, University of Wisconsin, Hector Rubinstein to NYU, and myself, I was going to MIT, but on the way I would go through CERN in Geneva. Now, a few days before boarding a boat to Venice, I took a boat because I had to bring back my car to Italy. I had an inspiration on going a little bit beyond what we had done all 4 together. And I kept working on the boat and then later at CERN till the end of July. And at the end of July, I submitted a paper to at that time was an important journal, still exists, Il Nuovo Cimento. Now, during that whole summer period, I was exchanging mails, of course, snail mails, about the development with Hector and with Miguel, and both, but particularly Miguel, reacted very enthusiastically. And in fact, Miguel would soon write one of his most famous papers, perhaps the second most famous papers, at least in this field, where he proposed the so-called, rightly called Virasoro amplitude. So my work and Miguel's became known as the planar and non-planar dual resonance models, respectively. Now, a few years later, I will go slowly, however, I anticipate what happened later. The planar dual resonance model was reinterpreted as describing the collision of open strings, that is, strings with ends, and Miguel's non-planar dual resonance model was instead reinterpreted in terms of the collision of closed strings. For those of you who have never heard about strings, the idea of strings is that elementary particles, instead of being point-like, if you look at them through a strongly magnifying lens, you see that they are one-dimensional objects. They can have ends and then are called open strings, or they can be just like a ring, oscillating, of course, vibrating, and they are called closed strings. Now, what is important is that at a qualitative level, this picture is still valid today, even if the strings that are relevant in the physics of strong interactions are much more complicated than the ones described by the V and V models of the 60s. But yet, even now, an open string is associated with mesons. Mesons are states with a quark and an anti-quark at their ends, at the ends of the string, and they're held together by gluons, particles which are responsible for keeping the quarks confined. Instead of closed strings is associated with the so-called glue balls, which are entirely made by this glue, this gauge particles. Now, both should exist, in fact, as bound states of the correct theory of strong interaction, quantum chromodynamics, at least in a suitable limit. This is a picture to illustrate what I have just been saying. This is the planar or Veneziano amplitude, which you see can be drawn on a sheet of paper, so it's planar, and you can visualize the process on the left as describing strings with ends which interact, join, and split. And for the non-planar, the strings are like these little circles. Again, they can join, form a bigger one, which then can break up and decay. Now, since then has been a huge shift of paradigm on string theory, and in this in retrospect, this was largely due to Miguel's work. And actually, it was due to his most famous paper in the field, the one on the Virasoro operators and their algebra. So far I have been very discursive, but let me go now a little bit deeper into the history of those crucial years, 2 years, 69, 70, that largely through the work of Miguel, planted not only the seeds for the birth of string theory, but also the seeds for what is known as the 1984 string revolution. So the story goes as follows. There was a big worry, in particular, Sergio Fubini was very much worried about this, which was based on previous experience, that possibly, in order to satisfy all the desired properties, those dual resonance models had to contain what are called ghost particles. These are particles which would be produced with a negative probability, and since nobody can make any sense of a negative probability, the dual resonance models would be clearly inconsistent, and the story would end immediately there. Now, to answer the question whether really the dual resonance model had predicted ghost particles, one had to first identify all the predicted particles of the theory. This was done already at the beginning of 1969 by Sergio and myself, independently by Bardacci and Mandelstam. And the result turned out to be both surprising and worrisome, because we were expecting the number of states of a given mass, m, to grow like a power of the mass. This was based on other examples, but instead it grew exponentially. So the number of states grew like the exponential e to the power m divided by some mass scale m sub s. S here stands for string, but of course in those days we did not think in terms of strings. And sure enough, among this exponentially large number of states, there were many ghosts among them. In fact, an infinite number also of states of negative norm produced with negative probability. Now, the Fubini, Veneziano, Bardacci, Mandelstam counting of the states was cumbersome, and it was soon replaced by a much more handy formalism, which was done by us with David Gordon and Nambu, the Nobel Prize. In that formalism, the whole set of states consistent of the energy levels of an infinite set of decoupled harmonic oscillators. Now, this may sound very complicated, but it's actually going back to, the first exercise in quantum mechanics. The first thing you learn in quantum mechanics, the first application at the levels of the harmonic oscillators. And this infinite set had quantized frequency. So there was something like a first harmonic, second harmonic, third harmonic, and so on up to infinity. So people know a little bit about quantization of the harmonic oscillators. They know that there is a nice formalism due to Dirac in which the states are obtained by acting on the ground state with so-called creation operators, which actually excite the lowest energy state. And similarly to what happens in the non-relativistic harmonic oscillators, in this relativistic case, instead of the energy, the square of the mass of the string was given by a typical formula for the energy of an harmonic oscillators, except that there is this sum over n because there were an infinite set of harmonics. And there is also an index mu, a Lorentz index mu, because it was not a one-dimensional harmonic oscillator, but the string, of the objects lived at that time in 3+1 dimensional space. Now, what was needed for Lorentz covariance, but was really the source of all the worries, is the fact that the commutation relations of these harmonic oscillators, which for the simple harmonic oscillators, I remind you, are commutator of A with A dagger equal 1, was a little more complicated because when mu and nu were identified with the direction of time, then the commutator had the wrong sign, had this -1. I copied back this, this formula in this slide. So in fact, n, I remind you, is the harmonic index, and mu, which goes from 0 to 3, 0 for time, 1 to 3 for the 3-directional space. So they had this wrong sign of the time-like commutator. And this was the source of the problem, namely states created by an odd number of time-like operators were actually ghosts. So was the dual resonance model doomed? It looked like, because the prediction that it must contain ghosts looked to be there. Well, almost. There was a tiny hope. All those states that we had identified and were described by these harmonic oscillators were sufficient to explain the processes, but perhaps only a ghost-free subset of them was actually necessary. This we felt in analogy with what happens in quantum electrodynamics. If you quantize the electromagnetic field in a Lorentz covariant gauge, there are some non-physical longitudinal photons, and they tend to be ghosts as well, but they can be gauged away. They can be removed by fixing some symmetry. So in the Fubini-Veneziano original paper, we had identified some of these unnecessary states. They were states created by applying a certain operator, which was later called L-1, on any other state. And all those states turned out to be unnecessary, spurious, as we were calling them. And this was probably sufficient to eliminate all the ghosts created by the time component of one of these infinite set of harmonic oscillators, the one with the label 1. But what about all others? So the situation looked almost desperate, and that's when Miguel's paper came. I checked if it was written in December 69 and published in 1970. He made a crucial discovery. He found out that if a certain parameter alpha 0, sorry, I forgot to point out, this alpha 0, as you can see in this slide, is a little bit like the plus 1/2 that you have in the energy of an harmonic oscillator. The ground state has not zero energy because of the uncertainty principle, and the ground state has an energy 1/2 h bar omega. So the analog of that 1/2 h bar omega is this minus alpha 0. Notice the minus sign, by the way. A little state. So if that parameter alpha 0 was fixed to be 1, it didn't look very good because of that minus alpha 0. One could enlarge enormously the space of these spurious states. And instead of having a single L-1, which generate all these decoupled states, it would generate, there would be an L-m with now m any positive number, okay, from 1 to infinity. So that has at least the potential of eliminating all the ghosts. And this was quite a hard exercise, but it was finally proven to be the case by Goldstone, Goddard, Goldstone, Raby, and Thorne, and independently by Brouwer a few years later. As it turns out, the Virasoro operators satisfy also a beautiful infinite dimensional algebra, the celebrated Virasoro algebra. In his paper, Miguel did not write the algebra, but I want to stress that the algebra per se is not the most important part of his discovery. And the far-reaching physical consequences are really in the paper itself. Well, I can make a short story of the Virasoro algebra, but perhaps I can also skip it, but it's an interesting story because Sergio Fubini and myself understood what was behind this Virasoro operators, and we even guessed that they had to do with these differential operators, Lm associated with z to the n plus 1 ddz, and then we simply blindly commuted these operators to find the algebra, and we forgot an important quantum deformation. I want to give tribute to Joe Weiss, who was at Berkeley, died very young in a mountain accident near here in the Mont Blanc. He saw our preprint, he wrote to us about our stupid oversight, as we explained in a note. Anyway, coming back to the importance of Miguel's paper in the development of string theory, I should just mention at least the following. One is that the interpretation of the dual resonance model as a string theory crucially needs the Virasoro constraints in the algebra, because it is thanks to these Virasoro constraints that you can remove the unphysical vibration of a string. So if you really want to associate with those mathematical formulae a physical object, a string that vibrates, you have to get rid of some fake vibration modes, which are nothing but a parametrization of the vibration, a change in the parametrization without changing the physics. So those modes have to be projected out, and it is precisely the Virasoro constraints that do that. So absolutely crucial. Now, the condition alpha 0 equal 1, as I said, is not very good. I mean, it sounded actually very bad from the start, because it implies two unwelcome consequences. The presence of a tachyon. I told you in the harmonic oscillator, there is plus 1/2, and here there is a -1. And this -1 is not appearing in the energy, but is appearing in the square of a mass. Now, a particle whose squared mass is negative, you can see that it has a momentum which is larger than the energy, so it travels with a speed larger than the speed of light, and therefore it was called a tachyon. Fortunately, this problem was later cured in supersymmetric extensions of string theory, so the very nice work, GSO projection, and so on. So fortunately, this problem could be solved later. Now, then, however, there is another consequence, which implies that there are also massless particles. Because of that mass formula, you can see immediately that you can cook up a state which has 0 mass at the expense of using those harmonic oscillators, but those harmonic oscillators carry a Lorentz index. So the state which has 0 mass has spin. So the presence of massless strings with spin 1 for open strings and spin 2 for Virasoro's closed strings. So in spite of many efforts, this time nobody succeeded in avoiding these states. I mean, while the tachyon could be eliminated, the presence of these massless spinning strings could never be solved. Now, this meant, unfortunately for some of us, the death of the hadronic string. Why? Because of the short range of strong interactions. Strong interactions are short-ranged, and that can only be explained by the absence of massless, strongly interacting particles. So that sounded a big, big blow. However, the fact that, in fact, string theory needs massless spinning states led already in 1974 Scherk and Schwartz to propose a reinterpretation of string theory, not as a theory of strong interactions. Now I may sound paradoxical. You can ask me a question later if you want, but as a quantum theory of all interactions, including gravity. Why including gravity? Because the spin 2 massless closed string of the Virasoro sector will be now interpreted as a graviton, which is the carrier of a quantized gravitational interaction. This possibility was confirmed by Green and Schwartz 10 years later and marked the renaissance of string theory. So string theory was basically abandoned because of the problem created by Virasoro, and it was abandoned for about 10 years actually, and then, came back to life because of this reinterpretation of the theory of gauge interactions and gravitational interactions. So Miguel's work was really at the heart of all three phases of string theory: its birth, its death, and also its resurrection. This ends basically my story of those magic 5 years, and I will only add an episode that not many are perhaps aware of. When Miguel's 1969-70 paper appeared, Sergio Fubini, who was then full professor at MIT, was so impressed that he asked and obtained from his colleagues permission to offer right away Miguel a staff position, I think, assistant professor, something like this, at MIT. For some reasons I never quite understood, Miguel opted for an offer from Berkeley and moved there in 1971. And since then, our wonderful interaction, but not our friendship, I want to underline, slowly faded away. But he kept doing first-class research, as you just heard in the previous talk. Well, I'll stop here. Thank you very much.
Okay, thank you. Thank you very much, Gabriele. And so we take questions from the audience here in the classroom. Apparently we have none. Let me see on YouTube.
I have a comment, if I may.
See.
Hello?
Yes, I can hear you.
I don't know if she can. Silvina, can you hear me?
Yes, yes, Eduardo, please.
Yes. Okay, so this wonderful algebra has had an enormous life outside particle physics as well.
Yes.
In particular, in the theory of phase transitions, and remarkably, even the theory of the quantum Hall effect. I still remember back in 1983, we were in Chicago discussing with Nambu and Leo Kadanoff the theory of the Laughlin wave function of the ground state of the fractional quantum Hall effect. And it was written on half of the blackboard. And the other half of the blackboard, Dan Friedan came and wrote the Veneziano amplitude. And then we stared at them and said, well, but they are the same equation. and so why is that? So we had a very long discussion, which at the time could not be sorted out. But the reason has to do with the hidden conformal symmetry associated with the excitations of the states, and which are governed precisely by the Virasoro algebra.
Yes, absolutely. Thank you very much. Yeah, I should have, first of all, emphasized that, of course, this Virasoro algebra led to important developments in mathematics, Katz-Moody, all sorts of things, but also the application to condensed matter physics. In fact, Sergio Fubini, in the later part of his life, was very, very fond of using the same techniques that had been used in string theory precisely on condensed matter. And I don't know if you know, but he even wrote papers, I think, on the application to the quantum Hall effect.
Yes, I am
And
familiar.
indeed, there are, yeah, one. Now, I have not followed the development afterwards, but as far as I understand from what you say, it has brought fruits.
Oh, enormous fruits. This is the way one writes down the so-called ideal wave functions for all of these topological
Yeah,
fruits.
the Laughlin. Yeah, yeah.
Essentially,
Oh,
you have to use
fantastic.
all of these structures.
Yeah, send me some references.
Not only that, the central charge of the algebra is what controls the thermal conductivity of the edge states. So it can
I
be,
see.
it can
So,
be
so you see, to miss it, it was a bit blunder on,
yes, so
on
the
our
central
side.
expression is crucial in all of this.
It was so stupid, you know, you guess and you don't check.
Okay, that was my comment.
It was a lesson for me. Thank you.
Okay, thank you, Eduardo, and thank you, Gabriele. And
You're welcome.
I don't think there are any other questions. So is there anybody here? No, that wants to ask? No. So we thank Gabriele again for the very nice talk.
Thank you for listening.
And so now we will have a coffee break. If you wish, you can have your coffee. We won't ship it to Europe, but
Okay.
have a coffee break.
I'll have my coffee as well.
And pause
I will
the
come- I will
YouTube
come.
transmission
And the
until
drink.
11:15 a.m.
If you want mate, I'm here. I have mate.
Oh, mate. Eduardo is sending mate. Thank you. El único que no está Gabriel es veneciano. Ahí le voy a hacer un chat. No, pero tenemos 31 en YouTube. Yo diría que mejor en inglés porque no sabemos qué necesitar.
Hola, hola. ¿Se escucha? No. No, no. Hola. Sí, 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 está prendido. No, no. Ahora sí, ahora sí. Listo. Espera. ¿Ahora? Ok. Dale, dale. Sí.
Okay. Good morning and welcome back. It is a pleasure now to have Andrea Solotar, professor of the Department of Mathematics here in our school, who is going to talk about Virasoro algebras and cohomology. Thank you, Andrea.
Okay, good morning. And thank you very much for the invitation. Thank you to Silvina and Alicia. And sorry. So for me, it's a true honor to talk in this day, in this special occasion. For me, the name of Virasoro has always been kind of a legend. When I studied in, sorry. Well, when I was a student, during the dictatorship, it was kind of, I don't know, people talk about the time when Virasoro was the dean of the faculty, and it was something, well, quite magic for me. And so later on in my work, during my postdoc, I was working already in cohomology, and Virasoro algebras started to appear in the things I I was working in. and they continued appearing till now. So, well, I am a mathematician. I work in algebra. I work in homological algebra. So what I'm going to talk about today is the algebra, not the physical applications, and more on the algebra itself, not about, or just a little bit about representations. There is a lot of work in mathematics about representations of the Virasoro algebra. Oh, sorry. It is not working. Okay. Sorry, no puedo usar ninguna de los dos. I'm sorry. Sí, el teclado, pero el teclado que lo tienen no me lo toman porque no sé qué hace esto. Ok, bárbaro. Gracias. Okay, sorry. So I was saying that I will talk about the algebra itself. It's a very important subject in mathematics. And well, there are lots of papers already with Virasoro in the title. But Lie algebras, and in general algebras, well, Lie algebras in particular, let's go back. Yeah. Usually arise in different ways in mathematics. For example, as the algebra of derivations of unassociative algebras, also like vector fields on a smooth manifold, also as tangent spaces at the identity of Lie groups. And we should often think about the Lie algebra like being one of these things, okay? So the Virasoro algebra, as I said, is a very important mathematics. The title appears in more than 1,000 articles, Virasoro in the title. And it is an infinite dimensional complex, Lie algebra. And something happened. Thank you. And it is what is called a central extension. I will get back to these things later. Central extensions of the bit algebra, which means that being the universal central extension, it is unique up to isomorphism. So we don't distinguish between isomorphic algebras. They behave in the same way. They have the same characteristics. They are exactly the same for us, okay? So when you have an algebra in mathematics, I mean associative, Lie algebra, any kind of algebra, it may be defined in several ways, okay? So think about sets. When you have sets, you can define a set giving a property that characterizes all the elements, or you can define it explaining or listing the elements you have. Well, for algebras, there is something, let's say, analogous. You can define an algebra. An algebra is just a vector space over a field with a product, some kind of product, okay? Associative, Lie bracket, something like this, okay? So you can define it, or you can explain what the algebra is by giving a set of generators and relations that these generators satisfy, and then you will obtain all the elements from these generators. Or you can define an algebra through what is called a universal property. So it's a property that is satisfied by the algebra and that characterizes it in a unique way up to isomorphism. We can't distinguish isomorphism. And of course, there are many other ways of defining some particular algebras, but I'm going to focus on the first two ways for the Virasoro algebra. Okay? So we come to the definitions. And well, as I mentioned, it is from the mathematical point of view, so I hope it will be interesting for you. So as I said, it is the universal central extension of another algebra, which is called the bit algebra. What do I mean by this? Okay, so let's start talking about bit algebra or centerless Virasoro algebra. Okay, well, we take K is a field. Okay, characteristic 0, you can think about the complex number, okay, field of complex numbers. So the bit algebra is an algebra which is spanned by, I'm giving it by generators and relations now, okay? So it is spanned by an infinite set indexed by the integers, satisfying this relation, okay? It's a Lie algebra with this bracket among the generators. It is a very old algebra. It already appeared in some work by Élie Cartan at the beginning of the 20th century. And it can be seen as the algebra of derivations on the Laurent series on one variable, okay? And later, in the 30s, it has been also used and studied by Bit. This is where the name comes from, but for finite fields, okay? And in this case, it is the algebra of derivations of something different, not the Laurent series, but the derivations of this quotient of a polynomial algebra. You know, or no polynomial algebras, polynomials in one variable, where we ask, we are in characteristic P, set to the power P to be 0, okay? And this has a consequence for derivation. Okay, so some properties of the bit algebras. So a bit algebra is created by the integers, okay? It means that it can be split as a direct sum of homogeneous spaces. And in degree n, for each n, you have a one-dimensional vector space, okay? Which is spanned by the generator Ln. But some gradings, it is important to have a grading for an algebra, to study an algebra, because it makes studying the algebra much easier, okay? And there are some gradings that are more interesting than others. So for example, here, this is the case because the grading comes from what is called an inner derivation, which is the adjoint derivation by L0, okay? So making or computing the bracket with L0 of any other generator, they are all homogeneous, gives you a multiple of the generator, which is exactly the degree. And this is useful for defining the degree also. Okay. Another way of thinking about it is, as I said, as the derivations of this Laurent algebra, where you identify Ln, as we have, as it was mentioned in the previous talk, with this operator. There is, well, you can change the sign. Okay, so it acts on this ring by deriving with respect to x and multiplying by this factor. But from a more geometrical point of view, it can also be thought as the algebra of polynomial vector fields on the S1, on the circle, where you identify Ln with this operator. Okay? So this is for the bit algebra, which also contains a copy of SL2, complex SL2, which is a subalgebra spanned by these three generators. I mentioned that the Virasoro algebra is a central extension of the bit algebra. And which central extension, or what is a central extension of a Lie algebra? Well, here is more mathematical. You have a sequence of Lie algebra, meaning that you have the first one, this is an A, which is a subalgebra of H, and then you have a projection on the algebra G, okay? So H is a generator of G by A, okay? And we call it central when A is central in H, in the biggest algebra in H, okay? And moreover, since this is going to be the case for the Virasoro algebra, when A is abelian, you call it an abelian. You can look at this as if you have vector spaces. So suppose you just consider the vector spaces. So you have A, which is a subspace of H, which projects onto G, okay? So you know that when you have a subspace of a vector space, you have always a complement, okay? So you can think as vector spaces that H is going to be isomorphic to the direct sum of the subspace A plus the thing that is on the right, okay, the thing where you project. But this is just as vector spaces. So it may be the case that it is also as Lie algebra, but it is not always the case, of course. So suppose that you consider a section of vector spaces that you call sigma from G to H. So you come back from G to H, okay? And this map beta is a map from G cross G, from the Cartesian product of G cross G with G to A. And what is this beta? This beta is exactly the defect of sigma to be a morphism of Lie algebras. So if sigma is not only linear, but it is a morphism of Lie algebras, then this beta is going to be 0, okay? But this shows if it is a morphism of Lie algebras or not. And if you look carefully at beta, it is alternate, so like the bracket, okay, it changes signs when you switch the arguments, and it satisfies this equation. So when you turn around, you have kind of a Jacobi equation. But this means exactly that beta is what is called a two-cocycle of the Chevalier-Eilenberg complex. What is the Chevalier-Eilenberg complex? I will, of course, not give you the details, but it's the complex that is used to compute the cohomology of a Lie algebra, okay? The cohomology of an object gives a lot of information, not only about the object, but about the representations of the object, okay? So sometimes you have an algebra and it is quite complicated, quite difficult, but if you can compute the cohomology, you have the necessary amount of information to study representations in a quite accurate way, let's say. Okay, so this is in degree 2 of the cohomology, is what is called okay. A two-cocycle in the Chevalier-Eilenberg complex. It may appear in the cohomology in degree 2. No te preocupes. El puntero. Gracias. Okay. Perfect. Thank you. And it works the other way around too. Okay. Conversely, suppose that you are not, you start from the beta, you start from the two cocycles, okay? So each time you have a beta satisfying these two conditions, being alternate and being and satisfying this equation, then you will have an extension of G by A, defined in this way, with the bracket defined in this way, okay? And suppose that you have two extensions. Well, maybe they are isomorphic as Lie algebras. The first one, suppose that it corresponds to beta. And the second one, suppose that it corresponds to beta prime, okay? So when are they going to be isomorphic? Well, when this is what is called a co-boundary one co-boundary in the Chevalier-Eilenberg complex. So the Chevalier-Eilenberg complex, or the cohomology of the Lie algebra, takes care of all the extensions of the algebra, okay? So this is why we, well, one of the reasons of studying the Lie algebra cohomology, okay? And well, we say that the extension is trivial if and only if it is isomorphic to H0, which is a notation I am using for the cocycle equal to 0, or let's say equal to 0. So now, just one more definition, I think. what is one extension is universal. Extension is, so suppose you have this extension here. It is universal if for any other extension of G by an algebra A prime, you have mapped here morphisms of the algebra such that if you go this way, it's the same as going the other way, and if you go this way, it's the same as doing this, okay? So this is a map of extensions. So the extension is universal when for any other extension you have a map like this. You can look at it saying that it is kind of an initial object among extensions. It sends map of extensions to any other extension, okay? Well, a consequence of being a universal object, in this case, a universal central extension, is that if such an object exists, then it is unique up to isomorphism. Then there is a unicity property because two of them will have the same property and then they will end up being isomorphic. Okay. One part is that if you have G a finite dimensional algebra, which is not our case here for the bit algebra, and you take A equal to C as a one-dimensional commutative algebra, then this is the cohomology in degree 2 with the coefficients in C, that is the place where beta lives. It is going to be 0. And this means that all the extensions are trivial in this case, okay? Fine. The bit algebra, for the bit algebra, it happens that if you compute the cohomology in degree 2, it is one-dimensional. It is parameterized by the complex numbers, okay? This is, well, that, as I said, you have a one-dimensional space of central extensions of the bit algebra, okay? And then the Virasoro algebra is one representative of this one-dimensional vector space. Well, you can pick which complex number you are going to take, and so we say it's a universal central extension of the bit algebra corresponding to a particular choice of this beta, which is going to be a complex number. And, well, there is this 1/12 that is kind of strange. Why choosing this one? Well, we are going to see in a moment why there is this 1/12 here. But before this, let me just mention that since it is a one extension by the complex numbers of the algebra spanned by this Lm, now you add one generator, and this generator is central, meaning that the Lie bracket with the Lm is 0, and you have that the bracket between the Lm has changed. It has been deformed by this last term here, okay? So this last term here is another way of saying beta of Ln Lm, okay? You put it here, fine. And as I say, the number 1/12 is chosen so that C acts as the scalar 1 on a natural irreducible representation that we are going, not the irreducible one, but we are going to mention now. So these formulas here in this part, give a presentation of the Virasoro algebra, as I said, by generators and relations. You have an infinite number of generators, and you do not need this infinite number of generators. It is called a redundant presentation. And there are several papers proving how many, trying to find how many generators you really need and how many relations you really need. And I think that the best one from the early 70s says that you only need 2 of these generators, that if I remember is the L3 and the L-2, for example, and just 8 relations, okay? So you can do this because you are more comfortable with this, or you can just give 2 generators and 8 relations. Okay. So the bit algebra is, you have a projection from the Virasoro algebra to the bit algebra. Through this projection, all the representations of the bit algebra are going to be also representations of the Virasoro algebra. But the other way around, it is not true, okay? There are representations of the Virasoro algebra that do not come from the bit algebra. Okay, and we are going to see now one of them. So let's go to this. I will mention now the Heisenberg algebra. So the Heisenberg algebra is, well, you can go up to the Heisenberg algebra by a procedure that is called constructing loops on any algebra. For us, mathematicians, constructing loops is just tensoring over the field with this, again, the Lorentz ring on one variable, okay? So you take a one-dimensional abelian, of course, the algebra, you do this procedure, and then you take a central extension. So this procedure leads to the Heisenberg algebra. What is now the Heisenberg algebra? Well, again, by generators and relations, it has, again, an infinite set of generators indexed by the integers, and one more, okay? This one more, H, is central, and for the other ones, you have this bracket, okay? Find a representation, an interesting representation of this algebra as the algebra of operators on this thing that is called B mu H, which in fact is the polynomial algebra in an infinite number of variables. And this mu H appear because you have to say how the generators act on this algebra, on this polynomial algebra, in infinite polynomial algebra. So the AN for n positive just acts as the derivative with respect to the variable. If your n is negative, here comes the H, and you have to multiply by this element in the algebra. And if you have n equal to 0, it just acts as multiplication by mu. So here you have the complete description of this representation. But it turns that the B mu 1 itself is a representation, in fact, of the Virasoro algebra, okay? And this is the example, I think this is the most well-known example of a representation of the Virasoro algebra, which is not a representation of the bit algebra, okay? So there are more things, and it is not a representation because of this relation. It is not a representation of the bit algebra. Okay. So some properties of the Virasoro algebra that are next to the properties of the bit algebra, because, well, it is a quotient after all, and it is that it is also graded by the integers, okay? And all the homogeneous components are one-dimensional except for the homogeneous component in degree 0. And now you have two generators, which are L0 and the one that is added, the C, okay? It is also nice, the fact that it comes from an inner derivation, the grading. As I said, this is useful, quite useful for computations. It makes them so much easier. And then this grading gives a triangular decomposition in the positive part, the negative part, and the what is called the Cartan part. okay? And the carton part is spanned by the degree 0 components. And the representation theory of the Virasoro algebra has been, as I said, widely studied, in particular by a very, very nice paper by Olivier Mathieu. So now, Hochschild cohomology, this is my area. So why Hochschild cohomology? Hochschild cohomology, you know, I mentioned you have different types of algebras, Lie algebras, associative algebras, commutative algebras that are associative also, and etc. Different kinds, Leibniz algebra. For each type of algebra, there is a cohomology theory associated naturally to it. Okay? For associative algebra, the natural cohomology theory is Hochschild cohomology. And it doesn't take care of, as I said, of the algebra itself, but of how are the representations of the algebra. And in particular, well, maybe this sentence may mean nothing to you, but it's defined as a derived functor. So why this is fine? Because it gives a lot of freedom to compute it, which is not the case for the Chevalier-Eilenberg complex, for the Chevalier-Eilenberg cohomology. Okay? So why do I like it in this case? Why do I mention in this case? Well, because, you know, studying the representations of a Lie algebra is not an easy task. Associative algebras are better in the sense that the modules, which are how we call the representations, have what is called the category of representations, has a lot of good things. In particular, when you are working with the representation of an associative algebra, you know, well, you all know vector spaces, okay? Vector spaces are fine, they have bases, everything is, we are all happy with vector spaces. But when we have something that is not a vector space of over a field, but a module over an algebra, a representation of an algebra, in general, you don't have bases. You no longer have bases, okay? And this is horrible. And so you want to get next to it. And so the idea is that, well, you are not going to have a basis, this is excluded for a representation, but you can split the difficulty of not having a basis in what is called a resolution. And this is exactly splitting the difficulty in maybe an infinite number or a finite number of steps, where in each step you have a basis. But all the difficulty is putting all these things together, okay? Well, you can do it in the category of representations of an associative algebra, okay? So this is why, for studying the representations of over a Lie algebra, what is called the universal enveloping algebra is constructed. This is an associative unitary algebra, which has the same representations as the ones of the Lie algebra you have, okay? And it has been proved that if you have by model a representation over this one, it is the same computing the Hochschild cohomology associated to the enveloping algebra and the model than computing the Lie cohomology associated to the Lie algebra and the adjoint representation, okay? Okay. That you can compute the cohomology of a Lie algebra using Hochschild cohomology, which is easier to compute. Okay. And in particular, you can study if a given Lie algebra has central extensions or not. Okay. Now to a subject that is more technical maybe, but it's a place where I have been, I have seen Virasoro algebras appearing naturally. And it's called, well, something that is called Gerstenhaber bracket. It's, I mentioned the Hochschild cohomology. It has a lot of structure, okay? So it has a product, which is graded commutative, it has what is called a graded Lie bracket of degree -1, which is a derivation in each variable, and all together is called a Gerstenhaber algebra. Okay, and in particular, with this structure, the thing that is in the first degree of the cohomology is a Lie algebra. Okay, and all the other things that are in other degrees are Lie models over this one. Okay, so this bracket appears a lot, gives a lot of information. We don't know exactly how many information it gives, but the problem is that, well, it is very hard to compute. Okay, so I am not going to give a formula for this bracket, but in order to think geometrically about it, let's look at a particular case. So suppose that you are in the commutative world, you have a commutative algebra. Think about the algebra corresponding to a surface in the space, or a curve, or some dimensional submanifold of a manifold, for example. Well, in the algebraic point of view, if everything goes well, meaning that if your surface is quite nice, it does not have just, for example, a point like this, or a crossing, or something like this, if everything works well, which is called being smooth, then it can be proved that this Hochschild cohomology is just the exterior algebra on the derivation of the algebra. And if you look at this side, the left-hand side, there is a bracket, which is called the Schouten-Neuhaus bracket. Maybe you have seen it sometimes, at any time. And on the right-hand side, there is what is called the Gerstenhaber bracket. And it is an isomorphism that preserves this structure. So you can think, if you want to think geometrically, as the Gerstenhaber bracket as an analogous, a non-commutative analogous of the Schouten-Neuhaus bracket, okay? Which is geometrical. So, as I was saying, up to a few years ago, it was very, very, very difficult for some intrinsic reason to compute the Gerstenhaber bracket. But this last, let's say, 6-7 years, there have been several improvements in the methods of how to compute these theoretical results, I mean. And so we have started computing this Gerstenhaber structure. And so a lot of Lie algebras appear naturally in this way, okay, and representations of the Lie algebra. And well, in my experience, I have two cases where the Virasoro algebra appear quite naturally as Gerstenhaber algebra, okay? So let me mention two examples. And this is the end. So my first example is what is called a quiver algebra with relations. You think of this point, you have arrows, the AI going from here to here, and the bars going the other way around. And then you have relations, that is, composing 2 is 0, composing 2 in the other sense is 0. And then you have a commutativity of doing this a lot of time is the same as doing this a lot of the same number of times. Well, these relations. These algebras are related, are what is called trivial extensions of Gentle algebras. And Gentle algebras, even if they have a very, very easy definition, and you may think that they are not interesting, well, they are related to triangulations of surface with functions, okay? And it is because of this that they are related through something that is called partially wrapped Fukaya categories to the homological mirror symmetry that is more next to maybe what you are interested in, okay? The Gentle algebras also appear as the algebras that are associated to some toy models of string theory Gayotto models. So, well, we don't know very much these algebras yet, but it is important to mention that they are related to homological mirror symmetry. And it happens that if one computes their Hochschild cohomology in degree 1, well, they are isomorphic as Lie algebra to a direct sum of copies of some particular quotients of the Virasoro algebra. Okay, so we have the impression that, well, I mean, we don't know yet the consequence of this on the side of the homological mirror symmetry, but it's one of the subjects that are intriguing now. So we are working on it. Okay, and then we are also able to provide the decomposition of the other cohomology spaces as a direct sum of simple models that, well, there are higher weight models appearing and this kind of thing. Okay. And another example that I will briefly mention is I have something. This is related to Hopf algebras. You know that Hopf algebras are kind of non-commutative and non-concommutative Hopf algebras are related to quantum groups. Okay, so this is a particular case that appears in the study of in the problem of classification of Hopf algebras. So you have an algebra that is defined by generators and relations like this, and if you compute the Hochschild homology and cohomology and you study the Gartenhaber bracket, well, you also recover the Kartantsov algebra plus the positive part of the Virasoro algebra. Okay, so one of the main problems that today, or problems people are interested is, well, what type of Lie algebras you obtain as Gartenhaber algebras of some algebra, and what does it mean in terms of the algebra? Okay, so this is the end of my talk. Thank you.
Thank you, Andrea. I don't know if there are any questions in the room. I don't know about YouTube. Are there any questions? Liz, are you watching YouTube or not? There are no questions? We have to open the camera. Okay. Okay. Y el chat acá no dice nada. Vamos a compartir. Okay, so if there are no questions, we welcome now the next speaker, who is, thank you, Andrea, again. And so next speaker is Enzo Tagliazzucchi. He's a professor at the physics department. He specializes in neuroscience, and we'll talk about deep learning as a metaphor of cognition. So.
Si dejaron el mismo nombre, decía Enzo Virasoro, el nombre de la charla. No sé si la cambiaron. Hay Virasoro Angie. ¿Mando de vuelta? No tengo la compu. Tenemos un... Para cerrar. Epa. O sea, se borrió de golpe. Bueno. Y al principio. Excelente. Estoy silenciado, creo, amigo. ¿Está bien? Y tenés el cosito para pasar. ¿Cómo? Buenísimo. Bueno, cuando me digan. Ok, tenés que poner capaz. Por ahí en Zoom podés compartir la pantalla de PowerPoint directamente. Deja de compartir un segundo. Sí, para poner compartir pantalla. Y ahora poner esa. Ah, eso sí. Y ahora, entonces, dale, capaz no sé si es. No, está bien eso lo está haciendo. Si no, pone compartir.
Para presentación en diapositivas no puede. Pero no.
Perfecto, se ve bien.
Right track. It was a bit too early, and I will show you how this research is conducted today and what are the main highlights of the use of deep learning, especially as a metaphor for human cognition. Deep learning is not only a tool to investigate the human mind, it's also a technological advancement that everybody is probably aware of. Today, most of the things that we interact with most of the algorithms that, for example, recognize images in the internet or even generate images from text, like this example here, are based on deep learning. So we know, of course, that Einstein never wore the Argentinian t-shirt and that Maradona never looked as bad as in this picture. This is generated by a deep neural network, which is called DALI. If you want more examples of this, I have a few on my first slide, and then we go to the real serious business. So these are some of my favorites. Of course, this is not working. This should work, right? Ojo, no, no sé, no pasan las diapos. Si no lo hago con el botón, pero me da paja. No. Ahí sí cambiaste, pero ahí funciona, So these are some of my favorites. This is a courtroom sketch of a capybara suing Elon Musk. So you see that here is Elon Musk and here is the capybara, or very serious in the courtroom. This is Ricardo Ford as a Mortal Kombat character. And this is the next president of Argentina, which I leave it up to you, up to your imagination, especially this one here on the bottom, who that person might be. So yeah, these are all examples that are made using DALI Mini, which is an algorithm that involves deep learning. So now to the serious business. I have 3 parts in my talk. Hopefully will be time for all of them. So first is a little bit history, and this is where I'm going to talk about Virasoro and his works. And then I'm going to work about science that is more recent, about the use of neural networks, deep neural networks, as tools to investigate animal vision, human vision in particular, but also as metaphors of language. So this is the landscape, a large landscape of the 20th century, and it shows different ideas or different methods or different theories or different philosophies about how to investigate the human brain, the human mind, and the relationship of those with behavior, also animal behavior. So starting early in the 20th century, the dominant school of thought was behaviorism. Behaviorism is very simple, but also very powerful, but very simple in a way. The idea is that we have an animal or the brain of an animal, and this is sort of a black box. We don't really know what's happening in there, but what we do know is the incoming stimuli that the animal is receiving and what happens. We know the behavior. So the idea, the behaviorist thoughts that if we can map all the relationships between all possible stimuli and all possible behaviors, that's it. That's all that we need to know about how the animal behaves. And that's basically the description. That if we find those rules, those laws that link the stimulation to the behavior, that's all that we need to know. So you see that there is a sort of problem here already. And this is addressed by the next generation of thinkers, which we could call the cognitive scientists. And the cognitive scientists, starting in the 50s and the 60s, they realized that this is not enough, because the relationship between certain stimuli and the behavior can happen in multiple ways. It can be like this, or it can be like this. There could be different processes inside the box that will link the stimuli to the behavior. And which one is actually happening, it's important, because it might take a different time, or it might, because it can influence behavior in other subtler ways that we are not really seeing directly, but it's important. So the main idea of the cognitive scientists is like this. Is in terms of philosophy of the mind, is called functionalism, and it is that these states, the ones I showed you before, but also the ones I'm showing you in this really complicated scheme that actually is taken from a paper by Virasoro, the idea that the mental states are only defined by their causal relationship with other mental states. So what makes this box here special? Well, it makes it special in the sense that it came before this box, and it came after this box, sorry, and came before these ones. So this is a bit like a computer works. The internal states of the computer are like this. They are defined by the next states they will cause and the states that were caused by them, basically. So the idea essentially boils down to that the brain is sort of a hardware, and that the mind is kind of a software. And in the same way as we can run the software, the same software in different computers, we could have minds running in different hardware, not only made of cells, neurons, flesh, but also made of different materials. So cinema has provided us very wonderful, really wonderful examples of this idea. In many movies, they take, this notion of functionalism, that the mind is sort of a software, and they show us different characters, different personalities, different individuals who seem to have minds like ours, but the minds are not unfolding in brains. They're unfolding in different systems. In the most extreme case, Solaris, the mind is sort of instantiated in a planet. The oceans of a planet, they have the same sort of causal relationships and the states as the states of the internal states of a brain. So this will have a mind. But at some point, the field started to question this idea, this notion that the brain is sort of a hardware computer, especially in its most strict way, which was called at the time Turing machine functionalism. And the idea was that this is that there is a very strict relationship between the computers that were used at the time, were Turing machines. There is a theoretical construct that is behind the notion of the modern computer, and minds. And the idea is that Turing machines are simply tapes of infinite length that they go sequentially to different states, and because of this, they can do sequentially different operations. And this was essentially the kind of model that many people thought that was appropriate for the mind. But this wasn't really the case, because we know that the brain and whatever is the emergent of the activity of the brain that we are at the moment calling the mind in the 50s and the 60s is not really like this. It's a highly parallel system with lots of connections that go in parallel. This is an example of the visual cortex of a monkey, and you don't really see that there is simply a single stream of operations that as time goes by, this is advancing and running the operations, but you have lots of parallel streams and lots of things going on in parallel. So the idea of functionalism sort of remained. The idea of the computer, the brain as a computer, was still there after this, but not in the strictest sense of a Turing machine. So then came what was called connectionism. Connectionism, the idea is that the kind of models that you need to model to capture the basics of the mind and the brain are not like the Turing machine, but they are more like the kind of neural networks that we actually see in the brain. So of course, why not actually go and look in real brains and see how they do these computations, and they get inspiration from that, and then build our models, which are sort of computers, but not strictly Turing machine computers. They are neural networks that compute things. So this is the idea of connectionism. And this is where the time where I started finding papers published by Virasoro at the time. And the very early papers were like this. This is the ultrametric organization of memories in a neural network. And this is from '85, the start of more or less the time where people started to think about these ideas, connectionism. But if you read the paper, this is a theoretical physics paper. This starts, with the energy functional, and then starts doing computations on this. The neural network that Virasoro was working on was a Hopfield network, which is sort of a generalization of the Ising model. So he put all his knowledge about spin glass systems applied to these kind of systems to essentially do a mathematical analysis of them. So this was in the '85. But then in the '88, I found this other paper, which was still a highly theoretical paper, but I started reading phrases like this. Prosopagnosia is a malfunctioning in the categorization process. The patient in front of the stimulus correctly recognizes the category to which it belongs, but is unable to recognize the individual. Prosopagnosia is a deficit in which you don't recognize the face. You are looking at the face of someone, I'm looking at Silvina, for example, but I don't know. I cannot recognize her. It's a deficit in some lesion in the brain. So he was essentially starting to think about the potential implications of damage to these networks as models of things that were actually happening in real patients. And then, if you look at one of the later his latest papers about this. The topic of the paper is not here, but it was already, the paper was something like neural networks as models for the mind. Pretty much similar to what I use as the title of my talk. And then you already read things like criticism to the kind of models which boxes connected together, like this Turing machine functionalism idea. And then you start reading more elaborate thoughts about what is the role of neural network models in cognitive neuroscience, and you start to see that there is a thought that is the main topic of my talk that is starting to mature, and the thought, the idea is that we can use these networks. They are not only interesting by themselves in terms of the mathematics, the physics, but we can use them to create concrete predictions about how the brain works, and we can use them as models of how the brain is processing information, but not disconnected from empirical data. We can actually create connections to experiments and make concrete validation of these ideas. This is not only a theoretical enterprise, but it's really in the direction of creating predictions about real neural systems. So this was 91, more or less. So by looking at these papers, I was really amazed, because I learned that Virasoro had a connectionist program of research to understand the mind. He started doing theoretical physics on these networks, but then he started slowly to think as a cognitive scientist. And he used methods from cognitive neuroscience to integrate the networks, to interrogate the networks. For example, he tried to simulate damage in the networks to see what happened, in the same way that cognitive neuroscientists use vision studies, people who had strokes, for example, to see what happens and to see how this is related to cognitive function. So the methods are similar, but they are applied to artificial neural networks. And then he even attempted some empirical validation using behavioral data. So data about how humans do tasks, for example. But also, in a way, it was a bit too early, because this was the 90s, and for this program of research to mature, as it is maturing today, there are a few ingredients that are missing. First, there is computational power. So these are GPUs. This is a GPU farm. This is the kind of technology that today we use to train deep neural networks, and it did not exist in the 90s in the same way that it exists today. Then there is the internet. How are you going to train these models with lots of information? Well, where are you going to get that information from? In the story that I'm going to tell afterwards, it will become clear that we have today lots of huge databases of images, for example. Where are these images coming from? Well, from the internet, from images that are being shared by people in social media, for example. So internet is basically a way of gathering together lots of information that you need to train more complicated models, neural network models, that can actually do stuff with the performance comparable to the human performance, which is something that the neural networks that Virasoro was researching could not do. And then, if you're really going to follow this to the extreme and say, okay, we're going to try to find correlates between how these neural networks process information and how the brain processes information, we need ways to look at the human brain, what's happening in the human brain in real time with neuroimaging. So methods from neuroimaging, like functional magnetic resonance imaging, only started to appear early in the 90s. So all these things weren't available to Virasoro, but there are things that in the next slides that I'm going to show, it will be obvious that we need them. But I think that it's important to mention that he was in an excellent track towards addressing some of these questions. So, yeah, so I will tell you a bit more about how this is happening today, how this program of research is going today in two examples. First, vision, and then language. If there is time, I hope there will be time for the last part. So, and to talk about vision, I will first start with a bit of background, the biological background of vision in humans and also in monkeys. The idea is that in the 50s, more or less, people knew that here in the back of the brain, there is something called the primary visual cortex, and there you have cells, neurons, that will fire to things that happen in specific locations in the visual field. So something that's happening in a certain place here will make a certain neuron fire here, but if you move around, there will be different cells in V1 firing as a response. So in the 50s, people knew this, but did not know exactly what made the cells fire. They knew that they respected, they followed the field of vision, but exactly what happened in each portion of the visual field that made one cell fire and not another one was unknown. So these two scientists, Huber and Wiesel, were doing experiments trying to find out how this happened. And I want to show you the video at the moment, but this is really, it's a really amazing discovery. The idea is that they were trying to show using slides of transparent paper to put in this old machine, you know, that people used to show slides, different sort of drawings, different sort of geometric images, objects, to see if the cells responded to those objects. And they couldn't find any. They couldn't find any object that could make a specific cell fire. But they realized that whenever they put the slides on, regardless of the object that was on the slide, whenever they put the slides, there were some cells that were firing. So they realized that the cells were firing to the edge of the piece of paper, not to what was on the piece of paper itself, but just to the line, to the segment that was made of simply the border of the page. So this is a very short video that will show how these people work. So there is no audio thing, but they are essentially telling you what I just told you. And what they have is some loudspeaker that's connected to the electrode. So whenever the cell fires, they listen to some sort of like this. So there they start listening to the noise because the edge of the piece of paper is entering. And then whenever the circle is there, they lose the sound. So they discover that there is a cell that is responding exactly to lines that are oriented in this angle. And this is how they discovered that cells in V1, simple cells in V1, respond to oriented segments. And they got a Nobel Prize for this, together with Roger Sperry. So these are Huber and Wiesel. They discovered essentially then that simple cells in the visual cortex, they respond to oriented segments. For example, here's an example of a cell. This is the trace of the electrode. And you have here segments with different orientations. And here you have an example of a cell that will respond to a segment that is oriented vertically. You have here the largest amount of spikes. And then you can create a plot like this. You can get the amount of spikes and the orientation of the segment, and you will find a tuning curve, something like this, that will have a maximum here, in this case, in 90 degrees. But if you take a different cell, this plot will be different. So you have essentially edge detectors in the very base of the visual cortex. And then what happens afterwards? When they discovered that there are other cells, which they called complex cells, because they were more complex than the simple cells. And these complex cells, essentially, they fired to either segments that were moving in different directions, or even to compositions of segments, so like two segments put together. And they essentially realized that the best explanation for this, or the most parsimonious, or the simplest explanation for this, was to assume that the visual cortex is a hierarchical system. So there is first you have cells that are simple cells that will, in given parts of the visual field, because of the projections to this other region, which I did not tell you about, but it's the lateral geniculate nucleus, which is a relay in the thalamus. But depending on how these positive and negative synapses are projected to the lateral geniculate nucleus, this will detect an oriented segment. This is a simple cell. This is the cells I showed you before. But then there are complex cells which receive the input of these simple cells. And because they receive the input of these simple cells, they can compute more elaborate things. And in this case, they can compute the movement of segments. So they're essentially first cells that do the most basic stuff to detect the edges. And then you have more complex cells that receive the input of these other cells, and they start to create more complex, to respond to more complex situations, like segments moving or combinations of segments, and so on. So visual perception is hierarchical. That's the message. So we have B1 here on the back of the brain, which is responding to segments. And then what we have is a progression of different regions in the cortex, B2, B4, and inferior temporal cortex, which respond to progressively more complex stimuli. So here we have segments, then we have combinations of segments, then we have more complex combinations of segments, and finally, in the end of this hierarchy, in the end of the temporal lobe, we have cells that respond to specific objects or even to specific concepts. So the famous grandmother cells. You have cells that will respond to the face of someone you know, for example. So this raises lots of questions that can be attacked using computational models. Some examples of the questions are, well, why is this so discriminative? So how come that the visual system can tell between so many different objects or so many different categories? Then why is it so robust in their transformation? So if I look at the face and I look at the face in a slightly different angle, I will recognize the face anyways. So how come that the brain is capable of doing this? And why this is translation invariant? Why, if I see a face here, or a face here, or a face here, I can recognize it anyway, regardless of where it is in the visual field. So these are some questions that are complicated questions, but need to be answered in any serious attempt to understand the visual system. So there are at least two ways to approach this problem. One is what I call the bottom-up model, which is the biology first approach. And here the approach is you build all these complicated neural simulations of neurons in the way you know that biology tells you that they are wired in the cortex of an animal, and you try to put all the biological realism in there, and then you hope that you can interpret the end result as some sort of computation that is related to vision. And then you have the top-bottom approach in which you build a model that you already know that will compute what you want to compute. And then you try to see if in the process of learning the rules of that computation, some similarities between this and how the human brain works start to emerge. So in this case, it's easy to address a biological plausibility because you constructed this to be biologically plausible, but what does it compute is sometimes complicated to understand. And here you have, maybe it's difficult to show that these models behave in the same way as the human brain, but it's easy to understand what they compute because they are engineered to compute something specific. So I will address these kind of models in the rest of the talk, and I will show basically the idea of a bottom-up model as a composite of three things. First, a way of putting these units together, which is called architecture, which is essentially limits more or less the kind of things that you can learn with these neural networks. Then you have a target function. This is something that you would like to optimize in a supervised learning algorithm for the network to learn, to represent something. For example, in this case, images. We have n examples, n images. We have here the samples, the training samples that we give to the neural network to learn. And then we have here the labels. So we have essentially a metric of the loss. That is how many images I could identify correctly and I couldn't. And then this depends on the parameters of the network, which are the numbers that you want to learn to minimize this function, right? And then you have the learning rule. So a way to optimize this parameter that is usually almost always related to the idea of the gradient descent methods. So in this domain here in the architecture, the last decades, in terms of vision, of networks for vision, were dominated by convolutional neural networks. Convolutional neural networks essentially run an operation, which is called convolution, that you are probably familiar with, which runs a filter through an image, and by doing so, it can highlight certain features of the image. For example, this is an edge detector. This takes this image and detects all the edges in the image. And then after the convolution, there is an operation of pulling the different parts of the image, combining them into smaller and smaller representations. And the idea is that the convolution acts like edge detectors in the same way as simple cells detect edges in images in the brain. And then the pulling operation combines the simple cells in a similar way than simple cells are combined into complex cells in the visual cortex. So this is essentially the analogy that between complex cells and pooling operations and simple cells and the convolution operation. So essentially this works like this. So we start with an image, which can have different channels. 3, for example, if it's in a color image, we have RGB. And then we convolve each channel with a kernel, with a filter, as it's known as well. And we end up with a feature map, which is the result of this convolution operation. And then this is just an example of how this runs through the image and does the convolution. And then on here, we do the pooling operation. We combine the output of many of these different kernels into a single number. And this works amazingly well. So this is a competition, the ImageNet competition. And the idea is that you have to train your network to detect objects in a very large database of images. And this is the progression of the classification in the, so basically the error in the competition as a function of time. And all these here are mostly convolutional networks. And you see how this is going down. And in 2015, actually, the convolutional network improved on human performance. So convolutional networks can detect images now with better performance than the human and we humans can do. So this is a scandal. I mean, this is really the way in which convolutional neural networks change the field of visual of machine learning applied to vision is something that is unheard of. All these competitions they don't do them anymore because the convolutional networks won. Right? It makes no sense to do these competitions anymore. So these are some examples of convolutional networks. This is a network to recognize handwritten letters. This is the AlexNet to recognize between 1,000 classes of images. And this is the BGGNet, and all they have the same architecture. They are like funnels which start to because of the pooling operation, they start to become more narrow, and in the end they have dense layers which output a probability distribution for the 1,000 classes of images. So I would like to comment now on how we can use these things as models for human vision. And the question is, are they good models for human vision? Well, we can start first with some behavior analysis. For example, we can take in this paper, we have 2,400 images, and we have 2,050 discrimination trials between images. And we can do this either with a neural network trained to distinguish between the classes of images, or with animals like monkeys who are trained to detect if one image belongs to a class or another, or humans. And the idea is to see if the performance is similar between the neural networks and the humans or monkeys. And here what we have is a metric of how well the humans discriminate. And here we have simply a discrimination in terms of the number of pixels that are shared between the images. And we see that there are no correlations here because this is a very poor way of classifying images. But if we put now a convolutional neural networks, we see that across different categories of objects, there is a correlation between how well the humans do and how well the neural network does. And actually, we can construct these confusion matrices in which we have different categories of objects, and at the intersection, we have how well they were distinguished between primates like humans and monkeys and different neural network models. And you see that all these matrices are quite similar. So the performance between pairs of classes of categories between the neural networks and the humans and the monkeys are correlated, essentially. This works in the sense of classes of images. It doesn't work well for individual images. This is an interesting point. Next, we can see how noise affects the categorization for humans and neural networks. So we have humans seeing an object, then we have some degradation of the object, some noise added to the image, some loss of contrast, and then the human has to decide the category of the object, and we have the same for neural networks. So here we have how the category drops for participants here and for different models for a degradation of loss of color, basically switch to grayscale. Here we have how this performs against additive noise, and here to loss of contrast. And what we see is that they all change quite similarly against the degradation of the image, except the additive noise, which disrupts much faster the convolutional network predictions than in the case of the humans, which go slower. And then this is my favorite, we have visual illusions. So we have something that's called the Margaret Thatcher effect. The Margaret Thatcher effect, you know about this, is that when you have a face and you only invert the eyes, the face looks creepy. But if you invert the whole face, even with the eyes inverted, it doesn't look creepy anymore. So this doesn't look really like a face when the eyes are inverted. But if you invert and then you invert the whole face, you don't realize that the eyes are inverted. You probably know this illusion. It's called the Margaret Thatcher effect because they did it with a photo of Margaret Thatcher, you know. And then you can have an index, which is how similar these look to you and how similar these look to you. And then you can essentially create a metric of how inverting the image is restoring the similarity between the faces. And then you can compute this Thatcher index for humans, but also for the multiple representation, inner representations of the neural network. And you see that for the later representations of the neural network, this Thatcher index starts to grow. So early the network is just representing the pixels, nothing else. So there is basically no confusion. But when you look at the later stages of the network, the network starts to see the illusion, essentially. This is something that you can tell from this. Then we have how these networks represent features. So they start by representing edges. You can essentially ask what kind of image will maximize the response to one of the filters. And early, the filters respond to oriented edges, as in the case of the visual system. And then they start to respond to more complicated combination of things and even to parts of objects. So you can use directly this to compare with neuroimaging data. So you can look at the brain correlates. You can take the layers of the network, and then you can create for each pixel in the image of brain activity that you obtain when you show the same pictures to a human participant. You can create a predictive model, or it's called an encoding model, to see if you can predict the response, in this case of fMRI, functional resonance imaging, the response of the brain activity in each part of the brain based on the representation on the neural network when it was exposed to the same image. And what you find essentially is that you can predict in V1, in the earliest parts of the visual hierarchy, you have the highest correlation with the earlier layers of the convolutional network. And when you start moving to the layers that are afterwards, you start to find correlations with higher level visual areas. So this seems to show that the hierarchy of brain regions is somehow correlated with the hierarchy of layers in the representations on the hierarchy of layers of the convolutional neural network. So we have this. And then you can also look at the similarity of the representations. So you can have a representation of objects in terms of brain activity and also representations of objects in the layers of the convolutional network. And you can see if the two representations are correlated. So you end up with these huge matrices, which in their intersection, they show how similar is the representation for example, in the human temporal cortex between two pairs of objects. So similar the brain activity is, and you have the same in monkeys, and you have the same in a certain layer of a convolutional network. And you see that these three representations, these three matrices are quite similar. And then this is one of my favorites. Some criticism to this idea of convolutional networks was leveraged against the idea because of the idea that convolutional networks are susceptible to confusion, but adversarial attacks. This means that there are images that if you have a certain convolutional neural network trying to recognize objects, well, it always happens, and you can prove this result, that there will be a low amplitude pattern of noise that you can add to the image, so it will look the same to a human observer, but it will confuse the network. So this will not be a panda anymore, but the prediction will be a given. Here you have the same for a washing machine, and you can even do this in practice. You can do this even in practical applications. So you have here a banana, and then you place this weird sticker, which is designed to confuse the neural network, next to the banana, and the prediction changes to a toaster. So this is called an adversarial attack. And this doesn't look like it doesn't remind you of how the visual system works, because the visual system is more robust. Well, is it actually? You can think of adversarial attacks in humans, and this was done by the Google Brain team, and basically they show images for short times, like 60 or 70 milliseconds. So this is not enough for you to explore the image with saccades. You just get a very simple impression of the image. And this is This is an example. So this is an image that this is a dog, right? Only 30% of the participants will tell you that this is a cat. But if you add a very small perturbation to this image, and you only show the image for say 60 milliseconds, then all the participants will tell you that this is a cat now. And this is a very subtle modification. And if you flip the pattern, so just as a control, people will tell you that this is a dog again. So there are ways to do this kind of adversarial attacks in the case of human vision. So I have 3 minutes, so I will end with a very, very fast. I knew that maybe I wouldn't have time for this, but I'm going to very quickly tell you 3 ideas of how neural networks can be used to process language, and how we are actually finding now that the brain somehow is correlated with the representation of language in these networks. So of course, this is philosophical, but the main idea behind how computers process language comes from Wittgenstein, and the idea is that there is no meaning of the words independent of how you use them words together with other words. So the neural networks that we have to represent the meaning of words, they learn basically by assigning relationship between the context of words to specific words. So if the context of a word tends to be the same across a large number of texts, statistically, then most likely the meaning of the 2 words which have the same context are similar. That's the idea. So we have networks like word-to-vec, which creates embeddings of words, low-dimensional representation of words, which respect this idea. And the idea of meaning they have is related to the context. They learn the meaning by looking at the context. And these embeddings are vector spaces, so you can do fun things like, for example, get the representation of king, subtract man, and add woman, and you have the representation of queen, for example. You can do this sort of algebra with the representations. And then you have more complicated neural networks, which I'm not going to explain because I don't fully understand myself, with like GPT-3 and transformer models and things like, on top of this that I show you, they learn the context in the word. So it's not only the meaning, but also the which part of the word, the sentence the word belongs, and they will extract information based on this in something that's called the compositional layer. And these things are amazing. They can create language, they can create text that is really believable. For example, I ran in GPT-3 with the prompt today, we remember the life and work of Miguel Virasoro, and the rest is written by GPT-3. And it looks quite credible. I mean, at some point it starts to talk about Dominican Republic, and then, and this is another example. So here he became the best mayor of Los Angeles and the first of all mayors to ever, okay, but the text, it looks like, remembering someone. It's not exactly the same because the neural network doesn't know who Virasoro is, but the thing is there. So just to finish, this is my last slide. We can do the same thing. We can train encoder models like multiple regression models to try to predict the brain activity when we make, for example, participants listen to specific words based on the inner representation of the word-to-vec model, which is very simple and doesn't take into account the part of the sentence where the word is located, or these more complicated GPT-3 models. And what happens is that, first, if we just train a visual convolutional network with the image of the words, with the image, the word like dog written on the screen, and then we compare this with the response that was obtained using 2 different imaging methods, magnetoencephalography and fMRI. In both cases, we only get similarity between the representation of the network in the visual cortex. That's fine because we're looking at vision. But if we compare, make the person like, listen to the word, or even look at the word on the screen, but compare the brain activity to the representations in the word-to-vec network or in the compositional middle layer of a GPT-3 model, what we find is responses located in a distributed set of regions which we know are related to language. And the more we go in this direction, the more sophisticated the model is, and the more widespread activations we find, even in regions that we know, like the frontal cortex, that we know are involved in not only in assigning meaning to words, but also in processing more complicated sequences of words. So my conclusion is that, of course, deep neural networks are then meaningful models of cognition. This is, at least I could convince you of this, because they map as expected into brain anatomy, function, and behavior. And yet there are multiple divergences. So these are not perfect models, obviously. And one of the main divergences is something that Virasoro already knew, that the brain doesn't learn this way. The brain doesn't learn by examples, always at least. And the brain essentially is not a supervised learning algorithm in the way that these convolutional networks are. And we have this very nice part of a paper by Virasoro in which she says it's impossible, that there will never be time for the human brain to optimize all these parameters, not even through evolution, that there has to be a different mechanism that is different from gradient descent or its biological implementation, and it has to exist for the human brain to learn so quickly. Babies learn to speak much faster than all the predictions of supervised network models. So there has to be something else, but we don't know what it is. So I hope you enjoyed it.
Thank you, Enzo. And I don't know if there are any questions. Dante. Dante, pues, no sé, para que salga por YouTube. Dale, sí.
Yeah, so the question is, there is an Argentinian researcher, Rodrigo Quiroga, who has these papers in which he inserts electrodes in the temporal lobe of patients with epilepsy, and he finds neurons that only responds to specific concepts, like a face or a word, that, the face of Barack Obama, but also the word Barack Obama, or even some event that was related to Barack Obama. So they're extremely specific. And the question is, if there is something like this in the convolutional network models. And the question is, yes, it's at the end of the layer of the network. So you have all these layers of the network are basically hierarchical. So this is also why these neural networks work so well, because early in the day, people had to think what are the important characteristics of the image to feed to the machine learning algorithms. And these networks, because they have so many layers, what happens is that the early layers figure out what representation is needed for the next layer, so which features are needed for the next layer to optimize the classification. And this works hierarchically. So first, there are networks that are basically learning, filters that are learning something about the basic distribution of edges in the image, a bit like V1. And then you have filters that are responding to textures or even parts of images. And at the very end of that funnel, at the very end of all those layers, you have a dense layer, and there you have units that will respond only if a certain object is in the image. Doesn't matter if the object is, at a certain angle, or if the face is a bit rotated. They will respond if the object is there. If you train the neural network with images, of course, they will only respond if the visual representation of the object is there. If there is a dog, they will fire. And this is a bit like different dogs will fire, not always the same dog. The same way that the neural network, the networks in Rodrigo's paper will fire to different dogs. Of course, if you have, I don't know, the word dog written, they won't fire because they were not trained to do this multimodal association like the human brain was. But you have at the end neurons that responds to concepts, to different ways of representing the same object. So yeah, this is at the very end of the hierarchy.
Are there any questions on YouTube? Zoom? No. Okay, so I think we thank Enzo again. And now we are going to have a lunch break, and you're all invited to go to Laboratorio 1, and where we are going to have lunch. And you can keep on talking to Enzo, I guess. Okay, we are going to pause. Well, we are going to end the YouTube transmission because we will use another link for the afternoon session. Thank you.